Welcome to the video on the third law and entropy. Alright, so at t equals 0, so this is on the absolute scale, so we're at absolute 0, all thermal motion has been stopped, and in a perfect crystal, all the atoms or ions are in a regular uniform array. So by perfect crystal, we mean there are no imperfections of the crystal. Wherever the most thermodynamically favorable positions are for those atoms or ions, that's where those atoms or ions are. So they're in a regular uniform array. They're in those in the lattice positions within the crystal. So if that's the case, then this implies that there's no disorder in our crystal, and thus the entropy must be 0. So this is the basis for the third law. So this is consistent with a statistical view of the molecules, because if all the molecules are in a fixed position, because again, they're in our lattice positions, if all the molecules are in a fixed position, then there's only one microstate. All the molecules are in the ground state. So if there's only one microstate, and we know that the entropy is equal to K Boltzmann constant times the natural log of W, the number of microstates that we have, then the number of microstates we have is 1, because all of our molecules, particles, are in the ground state. That means we have K times the natural log of 1. Natural log of 1 is 0, so the entropy there must be equal to 0. Alright, so now we get to the Nernst heat theorem. So the entropy change accompanying any physical or chemical transformation approaches 0 as the temperature approaches 0. So the entropy change for some process goes to 0 as the temperature that process is occurring at goes to 0. Provided that all the substances involved are perfectly ordered. So provided that we don't have any imperfections in our solid crystals. So this means that if we arbitrarily set the entropies of elements in their perfect crystalline form, with no imperfections, to 0 at absolute 0, t equals 0, then all the perfect crystalline compounds have 0 entropy, because the formation of the compound at absolute 0 has an entropy change of 0. So this is basically what the third law of thermodynamics says, that the entropy of all perfect crystalline substances, regardless of whether they're elements or compounds, is 0 at absolute 0. So note that thermodynamically, we've just arbitrarily set the value of entropy for a perfect crystalline substance to 0 at absolute 0, just for convenience, simply for convenience sake. But a statistical interpretation, using the Boltzmann formula, that formula that I showed earlier, shows that the entropy is 0 if there's only one microstate available. So if there's only one microstate available, then our assumption here for the third law is justified. So there may be some cases where our assumption there isn't true, that there is more than one microstate available even at absolute 0. So that can happen when there's no energy advantage to one orientation over another. So if we have a diatomic molecule AB and we line them up next to each other. So if there's no energy difference between arrangements AB, 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 with our molecules in the same orientation, and AB, BA, AB, BA, where the molecules are flipped every other molecule, then if there's no difference in energy between this case and this case, then we have 2 microstates at the ground state, and thus W, the number of microstates we have, is greater than 1, because 2 is greater than 1. And so even at absolute 0, now W will be greater than 1, and now the natural log of 2 is not 0, and so now there's some entropy even at absolute 0. So if the entropy is non-zero at absolute 0, then we say that the substance has a residual entropy. So let's look at some things that have residual entropy. So ice, water ice, has a residual entropy of 3.4 joules per mole K. So this residual entropy is arising because of the arrangement of the hydrogen bonds between the neighboring water molecules. So if we look over here we have one way that the water molecules can arrange themselves in ice, as the solid ice. And so you note that if we look at any one particular water molecule, like let's say this one here, this oxygen atom has two covalent bonds to neighboring hydrogen atoms. So this oxygen is bonded to this hydrogen atom here, and that hydrogen atom back there with covalent bonds. So that means that the distance between those two hydrogens and the oxygen is short. And then it's got longer hydrogen bonds to this hydrogen over here that's on this oxygen, and another hydrogen bond down here to this hydrogen that's on this oxygen. So that oxygen has two covalent bonds that are very short, and then two hydrogen bonds that are longer. Now, the thing is that which orientation those two bonds are in, the two covalent bonds, as opposed to the hydrogen bonds, is basically random within the structure. It's not like the hydrogen bonds are always pointing one direction and the covalent bonds are always pointing another direction. There's a good deal of disorder there. It's basically random on a large scale. And so we've got each oxygen atom has two short OH bonds and two long OH bonds. These are the covalent bonds and these are the hydrogen bonds. And so there's some randomness as to which ones are which. And so there's going to be some randomness left over, some entropy left over, even at absolute zero. So that's why ice has this residual entropy. All right, so we typically report entropies on the basis that the entropy is at T equals 0. So that's what this S0 means. We're at absolute 0 for our entropy as being equal to 0. So the entropy is 0 at absolute 0. We call those third law entropies. And usually we simplify this to just say entropies. That's the assumption that we make when we just say entropies. We're assuming that we're talking about third law entropies where the 0 is at absolute 0. So if there's a substance in its standard state at temperature T, then the standard third law, the standard entropy or standard third law entropy, we denote this way. So we have a little naught there for the standard as is entropy, and we're at some temperature T. All right, so now let's talk about a chemical reaction. If we have some chemical reaction occurring, we may have a change in the number of moles of gas, or we may have a change in the composition of compounds. When that happens, we can change the entropy. And so the standard reaction entropy, the change in entropy involved when we have a reaction occur, is defined as the difference between the molar entropies of the pure separated products, so that's this term, and the pure separated reactants, that's this term, all in their standard states. Right? So that's why we have these naughts here on our entropies. And it's at the specified temperature, whatever the temperature that we're talking about is. So this is just like the standard reaction enthalpy. Right? So we've got our naught saying that it's a standard, R for reaction, and delta S means the entropy change. Now we're shortening that, so that's the standard reaction entropy. Is equal to this sum, all the sum of some of the entropies, standard entropies for our products, right? Standard entropies, molar entropies for our products. This is the molar entropy because of the subscript M, and we're multiplying that by this coefficient nu. And so that coefficient nu is the stoichiometric coefficient for the reaction, for the reactant or the product. So if we have 5 of those molecules involved, then nu there is 5. If we only have 1, then nu is 1, and so on. So this is just like the standard reaction enthalpy. So the standard reaction entropy is likely to be positive if there's a net formation of gas. If we're producing gas, gases tend to be very entropic. There's a lot of disorder there because all the molecules are in a random orientation. So if we're producing gas, then we usually have a net increase in entropy. If we're destroying gas, or there's a net destruction of gas, then the standard reaction entropy is usually negative. And so also note that the standard entropy of an element at some temperature greater than absolute zero is not zero. It's something positive. Right? There's some positive entropy there because as we get our element at some temperature above absolute zero, those molecules start to move, and now there's some disorder in the crystal, liquid or gas. And so this is different than the standard enthalpy of formation, because remember the standard enthalpy of formation reaction, for the formation reaction, we're assuming that at all temperatures the enthalpy of an element in its standard state is zero. We're not doing that here for the standard reaction entropy. The only time when the entropy of an element is zero is when it's at absolute zero. So that's an important difference. All right, so also note that if we're talking about cations or anions in solution, a cation in solution can't be prepared without a balancing anion, so we can't measure just, let's say, a hydrogen ion entropy, because we need some negatively charged anion around with it. And so they have to be reported, so the entropy for ions have to be reported on a scale in which the standard entropy of some ion, and we've chosen the hydrogen ion, in water is taken as zero at all temperatures. So we know the actual entropy of the hydrogen ion is not zero at all temperatures, but we don't know what it is, and we have no way of measuring it without some standard, so we've chosen some standard, the hydrogen ion. That's going to be our zero. We're assuming that's zero at all temperatures. So this means that entropys of ions in water may be either positive or they may be negative values. Right? Now, this doesn't mean that this is a real negative value. Right? These are just relative negative values. Right? We're reporting these as a negative value because it's the entropy there for whatever that cation or anion is less than the true entropy for the hydrogen ion. So we're just reporting these as negative values. Right. So that's the third law and entropy.